Welcome to Oceanit's No Limit Speaker Series. Oceanit is a mind-to-market company that creates innovative and disruptive solutions from fundamental science and brings them to market at scale, breaking the bonds of normal to solve the impossible. No Limits is a celebration of those that explore beyond the limits of tradition to impact humans and society. Today, we are honored to feature Dr. Tsai, a pioneer in composites whose innovations have shaped aerospace and advanced materials science.
So welcome to No Limits at Oceanit. We appreciate everybody being here, and there's a lot of people online, so thank you for joining. No Limits is a thing we started at Oceanit over 20 years ago, I think. So Oceanit is a mind-to-market company. We do fundamental science and drive it to market, and we create products and technology from those basic ideas. You can see more about it online. No Limits is really about how we learn from people that have done things that are beyond what's considered possible or normal. They're really interesting people because it seems after the fact, looking backward, it's no big deal, but looking forward, it's a huge deal because you're thinking differently. So what we are really trying to do is learn from them a little bit about themselves, the thing that they did that really changed the way we see things. And then the third thing is really about what the future holds. You know, as these technologies and capabilities roll out into the future, they have these interesting and profound ways to manifest that sometimes it's hard to even imagine. So it's always interesting to hear from people that started these ideas and where they see that going. But before we get too far along, some general housekeeping. Jen?
Yeah. Thank you, Pat. So just a couple of housekeeping things. We have a lot of our friends here on Zoom, so we're really excited to have them here. For our folks on Zoom, please remain on mute throughout the presentation just so that we can minimize background noise. This is all being recorded, so we will be sending out the recording after this event. If you have questions on Zoom, please type in the chat. We'll collect them and bring them forward during the Q&A session. And if we don't get through all the questions, we will be archiving the questions and then we'll get the full list to you, Dr. Tsai, after the event. And just as an FYI for the people in the room, if you do have questions, make sure you stand up and speak loudly when you present your question, and lunch will be served after the event at 12:30. Tara? So it's our great honor to introduce our distinguished speaker today, Dr. Tsai.
Thank you.
Thank you.
So I'm very excited to have Dr. Tsai here giving us a talk about his career and background. He's a pioneer in the composites and aerospace industry and is a professor of aeronautics and astronautics at Stanford. He's also a member of the National Academy of Engineering. So this all started when I read an article in one of our local papers about him winning a couple really prestigious awards this year, the Daniel Guggenheim Award and the Spirit of St. Louis Award. These are awards that have been given to other pioneers in the aerospace industry like Orville Wright, Igor Sikorsky, and William Boeing. So in reading the article, I also recognized his name from classes that I took in grad school on mechanics of composites, and was really excited that the article said that he lived in Hawaii, like kind of down the street. So we were able to get in touch, and he graciously accepted to come and give this talk. His story and background really resonates with Oceanit's mind-to-market philosophy. And it's especially relevant in today's world as the space industry and aerospace industry is kind of picking back up and becoming more and more of a hot topic and hot area to continue to research in. So thank you.
Thank you.
Am I supposed to start?
Yes.
Okay.
want to sit here?
Yeah,
Where would you like? Right there?
no, sit here. That's okay. Well, thank you so much for inviting me. And can I have the first slide? So I have three parts of the talk. As first, who am I and what I've done and what I think the future is. My family came from Yiyang. Yiyang is a little town in Hunan province. And the first generation started at 891 AD. And the tomb of the first person was here. And this is in Hunan province. And there was my son and myself. We visited the tomb. And that's been there since his death, sometime after 890. In China, there's a civil service exams. This is where those who wish to take an exam, you go into one of these cubicles and you spend 2 or 3 days there and write an essay. And the winning essay, this is number 1 essay, and this is what you produce. And this is the exam. If you know how to read Chinese, you can understand it's not so easy to be number 1, or not easy at all. So it turned out my grandfather, and he's a 33rd generation, and he was the only one in the village there that passed the exams. So for 1,000 years, nobody passed, so he passed it. And his father, who is my great-grandfather, was a bean curd maker in the village. Because the notoriety of passing this civil service exam, then he became the bean curd king. I think he's self-appointed bean curd king. Then he became a celebrity in the city, and then he raised 17 girls. When farmers have their girls, they don't help out, or they didn't help out, at least they didn't think they help out, so they give up the girls. They keep the boys. So they would give up the girls, there's 17 of them, to the bean curd king, who had a bigger living quarters. So that is, he raised those girls, and that was a karma that he bestowed upon the rest of us. So there was my father here, 34th. Then he had 4 sons. I'm number 3. And among what we do, there are 8 of us who went to Yale, so we're very proud of our Yale tradition. That is my father, myself, and my brother John, and our 2 sons and the 2 grandchildren, and also a cousin. So these are the 4 brothers, and we all lived to be in the 90s. These are my two sons. This is Mingxi, the older son, who is a management consultant. He works for a French company. And this is my chef son, who is cooking for some important people. This is our granddaughter, Lauren. Lauren is very famous among the young people. So when they have pictures, they always have dozens of them instead of just one. I live in Kahala Nui. I had good support from the people. And some of these people you may know. And they gave us support, not so much a technical support, but they gave us wonderful Chinese banquets and vintage champagne and caviar. So that would give us some good food for us to do our work. So I work with many people, and these are the people in the spot. It's about 16 of us. And what we do is fibers. We have examples here. Glass fiber, and the carbon fibers. Then the carbon fibers are made into what we call prepreg tapes. So these are the tapes we use to build structures. So what we talk about today is how do we convert the properties of the fibers into something you can build in the structures. To build a structure, you take that tape, you make that into a laminate. A laminate is just a stack of a plate with different angles. So the trick is to what kind of angles you do. The sort of structures we do, here is to the left is a fuselage. This is a 787 Boeing. The skin and the internal structures are all made of carbon composites. The other famous application is the fan blades for the engines. And the engines have to be strong and tough and also resistant to bird strikes. So it turns out, if you study how you go from the fibers to the laminates, it turns out that you have all the famous man-made fibers, carbon, these are high modulus fibers, Kevlar fibers, glass fibers, and you have flax, you have hemp. So it turns out they all follow a straight line. And this is the expanded on the plot on the log, so you can see the natural fibers here and the man-made fibers here. And they follow the same laws of nature. So it is very important. This is a discovery that we made. We didn't realize. We thought the natural fibers would be totally different from that of the man-made fibers. So if this, in fact, is true, then many of the things we learn how to do the lamination for airplanes can be applied to the natural fibers. And in particular, example like the wood. The only panels the wood industry make is plywood. The plywood is only at 090. 090 actually turned out to be a very limited, very bad choice of angles. And if you look at this 787, I don't think you'll find anywhere that they have a 090. So what we're saying that what we learn from the high tech in this region can go directly into the natural fibers, and then hopefully we'll make a better natural fibers than what they're doing now. So it turns out the whole idea of making things simple, making things simple is very important. because you can do your job better. So the idea is not how complicated you can make it, it's how simple you can make it. In the traditional practice that is done today, if you ask somebody else to talk about composites instead of me, he'll tell you to know the stiffness, there are 4 constants, and for the strength, there are 5 constants. Now, that is very hard. If you have 4 constants, you cannot compare one material with another because one constant could be higher, but the next constant could be lower. So the only way that you can compare properties, it has to be a single parameters. In other words, if you can find a single parameter, then it's very easy to keep track. If you have a multiple parameters to describe it, then it would be it's impossible to make it simple. So the question is, how do you find that it turns out the single parameter is called trace. This is the definition of trace. Trace is the sum of the 3 elastic constants. So this is the sum that matters if you know the sum. And that it turns out this is all the carbon epoxy composites, and these are the value. The highest trace value here is this material, the lowest is this material. So it turns out if you want to know the stiffness, how stiff a material is, all you need to do is a trace. Once you know trace, you know which one is stiff, which is not. So they call, some people have suggested they call it Tsai's modulus because it is something that people didn't realize. Now, when you do the laminate, I mentioned, for example, you have a 0-90, that's like the plywood. You can have different angles, 70, 7, 15, 75, and whatever you want. So when you do the laminate, it's like a pie, how you slice it. So each material, it tells the size of the pie. Then the lamination, it depends how you slice it. You can slice it 3 ways, 5 ways, or whatever it is. And there it represents is a 47, 3%. So that what we know is that for a given material, you have a size, say this is a 12-inch pie. Then depending on which material you want, then you would decide how to slice it. Now, if you change the material, the size of the pie changes, but the angles remain. How you slice is the same. So you have 3 materials, so you have 3 sizes, you have 3 laminates, you have 3 ways of cutting it. So when you design, you select the material, select the cutting, and it's very easy to understand. So you don't need the traditional way. You have 4 constants, and you have to go through very complicated calculations. So when you make it simple, and which will give you an example how simple it could be, there's a very famous aerodynamicist, Theodore von Karman. He has done many things. He's a professor at Caltech. He said that what engineers should do is use 10% effort to capture 90% of the phenomena, not the other way around. So that's a lesson. The question is, how simple can you make it, and how much can you capture? And in the case of trace, it turns out it captured not only one constant you need to know, and it does it the best, as accurate as any other way. The other thing is the strength. How strong is it? To know the strength, we have a failure envelope, and this tells you you have different orientations, 0 degrees to 90 degrees, so in between 0, 15, 30, 45, and so forth. So when you design it, in the middle, the common area, this is the first ply failure, and in the ultimate, it's the last ply failure. So you make a prediction, and it turns out on the bottom, and the way they do this, they call it Tsai failure criterion. Every software, commercial software will have this criterion and tells you how you make the calculation. So when you come to the design of carbon epoxy, so these are all the failure envelopes. Now, the important part is the current practice is called quad. A quad is the 4 angles they use are 0, plus or minus 45, and 90. Those are the plies, the fixed plies. But they are depending on how many layers you have. So you have 8 plies, you have this family, then you have 10 plies, you have this family, you have 12 plies. Every time you change the number of plies, your failure envelopes changes. So that is one of the problems, that there are dozens of number of plies. Number of plies could be as low as 4, as high as, there's no limit. You can high as 100, and so forth. So that it is so difficult and so complicated, and there's a better way of doing it. And so this one shows how good are the predictions. How good are the predictions? So the solid lines, that's the Tsai failure criterion, and the dots are the data. So that it shows that the calculation based on the theory, it works really very well. You can see how close they come to. And so you have 4 materials. You have 4 different laminates. So you test it. And first you do the theory, you know the theory. Then you test it. You predict what the value is and say this should be the difference between 558 versus the actual one. And you can see it is very close. So that we are introducing a new material where we do the traditional way is a quad, and we're introduce what we call double-double. Where the quad has 4 fixed angles, 0, plus or minus 45, and 90. So you change the number of those plies. So you have 8, you have 12, you have 16, you have 20, you have 32. And these are representative of all the orientation of your laminate. The problem with the quad, this is a quad, it gets how many stacking permutations do you have? Well, if you have 8 plies, there are 24 such stacking sequence. Then it becomes 600, becomes 10,000, becomes 160,000, becomes over 1 million. So that it is so complicated, so every designer, when they design something using a quad, each one of them will have a different laminate because there are so many permutations, hundreds of thousands. Now, we proposed what we call double-double. Double-double just have 2 sets of angles, plus or minus angles. For example, this will be plus or minus 0 and plus or minus 52. So this, you can see, there are 2 zeros and plus or minus 2. So you can have a different, so we match. Instead of having to this way, we do the double-double, they have the same stiffness and strength. But you can see it's so much simpler. And you go all the way down here, and instead of doing this, you can do the same thing, and you'll be plus or minus 16 or plus or minus 62. And the important thing is, everything you do here only has 4 plies. And 4 plies instead of, 32 plies. Everything is 4 plies. You see 4, 4, 4, 4, 4. And how many stacking sequences? There are 2, 2, 2, 2, 2, 2. And you can see the difference between this, how simple this is, versus how complicated that is. And you can see when you make the structures, if you use a quad, this is what it looks like, a quad. If you use a double-double, this is what it's like. Now, you can see the tremendous difference. And this we call a homogeneous, because it's the same. And this we call a heterogeneous, because everything is different. So what's the difference between homogeneous is what we want versus what is heterogeneous? So here we have an example. You have the pancakes. The pancakes you can have, we have 6, but you can have 4, you can have 3, you can have 2, you have a 1. And because they're the same, a 6 stack, 4 stack, they taste the same. And that is what a homogeneous is. Now, what's the example of heterogeneous? Well, belly pork. Belly pork is heterogeneous because belly pork at least has 3 parts. You have the skin, you have the fat, and then you have the lean meat. So you cannot slice it. You slice the skin, which is the best part, then it's not the same anymore. And this, incidentally, is the best Chinese comfort food. In fact, the best part is the skin and the fat. And don't eat the meat. But you cannot change it, so the heterogeneous is a bad thing. And when you're homogeneous, then you can slice it, you can make it fewer, you can reduce the weight. And that is the key. So the double-double, you can reduce the weight, whereas the heterogeneous, you cannot. So here is an example of the stiffness. The stiffness, again, you have 6 ply, 8 ply, and 10 ply. So they're from 3 different families. So when you design, if you change, you want to make as fewer ply because you want to make it lighter. The structure has to be light as possible. So if you go from 8 to 6, or 8 to 7, for example, you want to drop 1 ply, but then you switch a family. Within the family, you can find out what is the best. But if you switch from 8 to 7 or to 6, the best laminate is no longer the same. So you cannot really find out because there are too many, as I say, there are dozens of families, and you jump from one family to another, so you don't have the same criteria, which makes the design so difficult. And then on top of that, you have the hundreds of thousands of permutation in the stacking. So it makes a quad very, very difficult. So what does a double-double do? Double-double is 4 plies. It has only 1 table. This 1 table have 2 angles from 090 for the one, then you have the 090 for the other one. So what happened? Well, double-double is better because there's only 1 table for all laminates, and for carbon epoxy composites applies for all materials. And remember, we showed that the relationship between the fibers all follow the same. You can use the same table here, and you can do for the flax or hemp or glass as you can do with carbon. So it is one table instead of hundreds of tables. As you change the materials, you have to repeat it. So you have a fixed material, and you can rate them. And we will show you that was, if you have a single parameter, then it's very easy to rate them, which is better, which is stiffer. Then you can zoom. In other words, you have the angle between 15 and 30. You want to know what happened in 28. And this is a continuous function, so it's very easy to find out what the angles. And here, you want to know 7. It's very complicated. It's not that easy. And then you cannot. And then it's homogenize. Like the pancakes, you can taper. Then you can reduce weight. Then you can make what we call pre-applied double-double. And then you have a tape that has a preset angle, so you can increase your productivity by 6 times. And then you can have also a laminate that has a negative thermal expansion or negative Poisson's ratios. Now, the negative thermal expansion is very important because ordinary materials, when you heat up, it expands. When you chill it, it shrinks. And so people use shrink fit is to change the temperature so that they can insert one material into another at a low temperature, and then when it returns to regular temperature, then it becomes locked. But chilling is very difficult because you can put in your freezer. You can then have to go to liquid nitrogen. Liquid nitrogen is so you have a big gel. But if you use negative thermal expansion, you heat it up, it'll shrink. So you have heating is so much easier to do, and you have a better way to control your heating. You can go heating to 50 degrees, 70 degrees, or 80 degrees. You can do the shrink fit by a temperature variation. That's very easily done. So this is all the failure envelopes, and this is all double-double. This is double-double, and it's very good because this is we call master. Depending on the angle, say this one represents the 0 and 30, and this one is the 0.45, 0.60, and so forth. So this is a master, and this is the average strength, and then you can change to whatever materials, and these are the average strength, 360, 598, and so forth. So you can, this is what we call master. You change material, you just change a scale factors. I hope you guys are impressed. Next. So this is what you can do. This is called omega stringer. What else to show how you can taper? In other words, this is 32 plies, and this is 4 plies. So you can taper it, and how much you save 41% of the weight, because you really don't need anything in there. In fact, you don't want the same thickness because you have a very problem in the stress. So that tapering not only save weight, it makes this stringer stronger. Now, how do you taper? One way to taper, this is a famous Hawaiian airline deck, we call it card sliding. All you have to do is slide a card. So then one way you can see, you can taper, give you a linear taper. So linear taper is good because the car sliding, you will take all material with the same dimensions. Otherwise, you have to cut. Make a small piece at the top, the large piece at the bottom. So there are always simpler ways of doing it. And this is one example how you can do the car sliding, and then you can do the tapering this way. You put that in the tools, and then what happens is you save 41% of weight. So how much weight do you save when you try different things? You try fuselage, you try stiffened panels, your tube and wings, and there are different ways how you can taper it, and this is how much weight you can save. So you can see the numbers about half. You can save half. Half is a huge thing. If you go to Boeing or Airbus, you can save 2%, and they really will love you. But here we can go with a double, you can go very high. So then, what's the future? First of all, you find out the material. You have materials. I have 4 materials. One material here, T300, another material, T800, and I have a material, IM7. This is a double. This is the angle, 0 to 36 and 46 to 90. So for this material, you want to build a fuselage, and this is the angle you should have, which is plus or minus 32 and plus or minus 86. And this is done by a lab search. This is like a Google search for laminates. And then you want to do upper wing, lower wing, submarine, bulkhead, and shaft. So it tells you for these applications, there are different angles you need. So if you change material, it would be here. The values are different now. This is 783 and this is 3, so this is twice as strong. But the angles are essentially the same. And then you have, so you combine all the 3 materials, you put on the same chart. So it turns out there are 2 materials, 2 applications. Here's the wings, and here is the fuselage. So it turns out this one is 3090, which is the same as 060. You just turn it around 90 degrees. So if you have one tape, which is 060, you can do that for the wings, and you can use the same tape, wrap it around for the fuselage. So that these are the simplicities that you can do. It's not necessarily the optimum, but if you have only need one tape, one double tape, we say you do the 0 plus minus 60. So here's what happens. You can have the regular ones. You can have what we call a thin plies. This is a thin plies. What's the ratio between the thick and thin? About 5 to 1, 4 to 1 ratios. So this one we call it a new laminate. This is for the future, which is a pre-plied double. So what's so good about a pre-plied double? You can have it's like a metal. It's homogenized, but it has orthotropy, and the thickness increment is the same. And then it's simplified because it's homogenized. You can do the wrapping, taping. You just do one axis. In other words, you want to wrap around for the fuselage, you just do that. You don't need cross-plying. And then you have the ply drops. It's very simple. Then there's a way to make the laminate more pliable, because not everything you do is flat. There are things you can do. So the traditional approach using chopped fiber. This is a chopped fibers. Then you do the chop fiber, try to make them into some kind of a line. And that is really difficult to do because this has to be automated. You can't just pick one at a time and place it because there are thousands and thousands of chop fibers. So our approach is different. We say, don't chop it. You use a regular, and then you use a Gerber. You cut the ones, use a Gerber cutters. And so the advantage of that, then you can have any kind of pattern you need and so forth. So the result is this. Here is a Gerber cut. We have the same thing. The red is how you cut it. There are different ways of cutting it, but you don't use a stack chopped. You just do that, and then this happens to be a 1-inch square. So what happens is if you don't chop it, your tensile strength is 1,000, and then chop it this way, you only lose 20% roughly. So this is, again, a totally new way of doing it. And this particular one would be our favorite, the 0 ± 60. And you can do this. So this, again, would be a totally new way of doing things which we think can replace what they do now. Now, with the one parameter, that becomes very important. You can show the value of trace based on the relationship between the fiber stiffness. And this is a relationship for the fiber stiffness. So you can have the high modulus here and the carbon epoxy, Kevlar, glass, and then those natural fibers be down here. They follow almost the same linear relationship with a slightly different parameters you have to change. And this is the same thing with strength. The strength is a function of the fiber tensile, fiber compression. It shows that if you know the fiber tension, fiber compression, you can find the average strength of the laminate. So we have an example to show that suppose we take you have IM7 977, which has a trace value 218 and a factor of 117. You know these. You know this for all the materials, all the carbon epoxy. There's about 15 of them. These are all rated by single parameter. They're rated. It's only when they have single parameters then you can rate them. So how accurate are they? They're accurate. This is a coefficient of variation is about 3%, 2%, 1%, and so forth. So how good are your experimental? Your experimental is about 10%. In other words, your theoretical prediction is much better than you can demonstrate if you don't know what it is and you measure it, and you will have a much greater variation than that. So then it is very easy for you to go from the master stiffness. This is master stiffness, only one table. That's all it takes. One table here and one table here for the strength. So if you know the stiffness, you know we want to say 060, 060, our favorite laminate. So this is 060 for A11, 50%. And this is A22 is 29%. So you can get what is the stiffness in one direction is 109. And this one is just the same factor multiplied by trace. Trace, as I mentioned, is 218. And so you get all these factors. And this is about as simple as you can get. And then you want to know this, what is the failure envelope? Failure envelope is 861. but then you just multiply that by 1.17. So at this point will be the value here, multiplied by 1.17. So these are the values. So that with these two charts, you will be able to get any materials or any laminates within the double-double family. But this, unfortunately, you cannot do it for the quad because the quad, as I say, come from dozens of families. Then you need dozens of charts, whereas double-double is only one chart. And then this one shows how accurate is this. And we say this is 3 materials. Material, this is strongest, upper bound. This is the master, and this is lower bound. So you can see the variation. This is the same laminate, but the sizes are different. And the ratio between this is 1.25. The ratio between these two are 0.63. But if you change the materials, you add more zeros here. This is 1 0, this is 2 zeros, and there, that was black. It's the 3 zeros. And you can see the shape changes, but then the ratio, 1.25, 1.25, 1.25 is the same. And then you have this ratio between these two, 0.63, 0.63, 0.63. And these are just remarkable that they maintain the same. And then the difference between the two laminates, this one 1.06, 1.06, this is 1.05. So they're accurate less than 1%. So how do people do the test? So we have 2 ratings. First, the material rating. Material rating, this is the strongest material. This is the weakest material. This is the master. So you can see this is 1.25 of the master. This is 0.63. So you saw that on previous chart. So all these are the materials, carbon epoxy materials. So they all line up, and what the individual columns are is the change of laminates. So all the laminates, you can see they're almost all flat tops. So that you can have, for example, you change those 3 materials, the weakest, the master, and the strongest. You can see the shape is the same. Just the scale is different. The difference between the cell, this is 1.25, this is 6.3. Now, when you change the materials, when you change the laminates now, I'm sorry. Here is what the laminates, how the laminates are ranked. This is 1.35, 1.39, I'm sorry. This is 1, this is 95, and this is 6.3. So as you change laminates, it will change not only the shape, but also the sizes. So everything is locked in within something like 2% or so forth. So the question is, how many tests do you have to run? Because you have about 15 carbon epoxy material, you have about 18, 20. So the total combination, you have about almost 300 combinations. So when people do design, the difficulty is they have to run tests. The tests to generate allowables takes millions of dollars in 2 or 3 years. So now we say that is a case we call blind testing. They have no idea what the number should be. So that's what they test. But even if they get the data, they don't know if that's the right number or not. So it's very important people study what is the theoretical values. What is the theory? If you know the theoretical values, then you don't need to test thousands. You have smart testing. Smart testing tell you if I test this one I get the value. If I change the laminate, well, the factor is 1.39. All you have to do is, if it come out to be 1.39, and or close to it, then you should be very happy. So the testing will change. We say there's no a new strategy is whether you believe there is a connection. All the laminate and materials are tied with the fixed ratios, as we have shown in here, or you have no idea what the numbers should be, then you run them by the thousands. And we think we can do much better by recognizing there is a relationship, and these arrows are shown in here. This is like 0.42. In other words, this value versus that value is 42%. Now, the airplanes, there's this one airplane, this is called by auto aviation, Solari 5, and this is Solari 500. And this one is built with a skin that is laminar flow. In other words, less friction. So when these two planes run side by side, in fact, when they run this plane and run this plane, this is the chase plane. It turns out the same flight, the same distance, this used 129 gallons, and this used 27 gallons. So that you can do this with the skid, but you cannot have a fasteners on the skins. You have fasteners because the flow will be disrupted. You have a turbulence. So that this flight has two features. Once it has a double skin, you have the inner skin, which is pressurized. Then the outer skin is unloaded, so you can make that to facilitate laminar flow. And then there's a famous RAF, Royal Aircraft, Air Force, the Wellington bomber. This is the Wellington bomber. This was made 100 years ago, World War II. It's a unique, it has a grid as an internal frame. And the grid is so tough that the pilots love this plane. That's what we call the pilot's RAF favorite, because they can come back even if they get shot up like this. And then even they crash, it doesn't collapse. So it is a very tough structure of the grid. So the question is, composite airplanes. There are two composite airplanes. That is the Boeing 787 and the Airbus 350. And they can only make something like a dozen a month. But they want to go more because the market, they can do, if they can produce more. And then they have plans, they can go from 12 to 14, but it takes them 2 years to do. So that the lesson from our perspective is you cannot use the same method and expect to have miracles. So you have to go differently. You cannot do the same thing and expect to nickel and dime it and to be able to go from 14 and up. But the way they're doing it, they can never make it 30 a month. So that you have to make changes. So one way to do it is to follow the Wellington, make it out of a grid. And this grid is made out of stainless. not composite materials. Stainless is good because stainless you have a flat, then you use water jet to put whatever pattern you want. Then stainless is easy to weld. So that if you use this, then you don't need autoclave. Autoclave is a big oven. The way they are doing it now is they need an oven to cure it. So if you want to make something, there are two things you need to do. One is to do something outside the autoclave, and this is the stainless. This is one way to do that. The other one is not to use fasteners. They use millions of fasteners. The fasteners are expensive. The fasteners also does damage to composites. So then what can you do? This one, we say, do this. Stainless is outside the autoclave. Then we say, use double-double. Double-double has one advantage. You can have a negative thermal expansion. See, this is the plot of a thermal expansion. So depending angles, when you have a plus and minus, here is 0. Then this region here, you go plus and minus 31, it goes negative. As I say, the negative is good because you can make a shell with negative coefficients, then you heat it up, then you can slip that into the grid, and then when it comes, then will expand. That will give you the shrink fit. And the advantage of that is the internal skin. It will not, you don't have fasteners. And in fact, you don't need adhesive either. So there are many ways you can do with a double-double that can change. You can do negative thermal Poisson's ratios. Poisson's ratio, you pull on the materials, it shrinks, the diameter shrinks. Now, if what you pull on has a negative thermal expansion, you pull on it, it expands. So when you push on it, it shrinks. So that you can have a fastener, because you can pre-stress your fasteners. You put a tension on it, it will shrink. Then you can put that in, say, in a hole, and then you release it, and then it will lock in. So there are many things you can do that it doesn't happen. So in the end, we have all the books you can download. And this is a link you can download. These are the books on double-double. So then the conclusion is you have double-double. You have 4 constants. We have 1 constant. You have 5 strengths. We have 2 parameters. And then heterogeneous. This is homogeneous. This is a 4-ply layup. And this is 1 axis. And then you cannot scale, whereas this you can scale and zoom. And this you cannot use thin plies. And it's a perfect match for double-double, and so forth. So that in the end, there's no future in quad, and we think future is here. And just do it. Thank you so much.
Thank you. That was really interesting. I appreciated the drive to simplicity. We've been working on that here with the grammar of RNA, using Chomsky grammar to simplify complexity in a variety of areas. And so this kind of fits that quite nicely, that there's an elegant way to do it, or we can make it really complicated. And so you found a very elegant way to look at laminates. That's mind-blowing. We're going to have time for some questions. Tara, why don't you?
Yeah.
Open.
Yeah, if there's any questions in the room, we'll take those first, so you can stand up.
Yeah, I have a question. Forgive me, I'm not an engineer by practice, but I really like the idea of the negative coefficient of thermal expansion.
Yes.
I'm wondering how, if you have a piece of equipment or machinery that has this negative coefficient of expansion, is that a problem if your machinery then heats up? Will it just start to come apart?
Yeah, you got a right point. So you have to select the material and temperature range for you to do the shrink fit. That's outside the operating range of the materials. So for aircraft, the aircraft is between minus 50 to plus 100. And so that's the operating range. So you must do the shrink fit, say, from 200 to 400, so that you wouldn't go up there and suddenly it fell apart. I can understand that, yes. You should be able to control it, yeah.
Okay.
Yeah.
Other questions? Yeah.
One of your laminate selection charts had, wings, fuselage, but also submarines. Were you involved at all in the Titan submersible research after the effect?
Well, we have one for a submarine. That would be the same as a submersible. Yeah, I can't do the angles. The angle is more like plus minus 30 and plus minus 60 or something. But those are very easy. We have this tool called Lam Search. Lam Search is just like Google. You can search anything you want. This one just tells you if you know the applications. Say you're a deep submersible, and you put in the anticipated stress, and then we'll give you the answer. That Lam Search. We did the Lam Search. It's very easy. So whoever wants a Lam Search will be happy to send it to you. It's an Excel program. Yeah.
We have an online question. What applications of double-double are you most excited to see in the future?
Well, we like to get the big things. We like to see if we can impact on the design of fuselage and design of fan blades. So because the impact will be huge if we can find a better material, and the engines for the big planes is $20 million. So you much rather do something hopefully can make it a better $20 million thing than something like $2,000. So that is the sort of thing we're looking at. But it's not easy because fan blades has not only you need to go through a lot of tests and also certification, because the reliability and safety issue takes a long time to do and to get the approval. But if we can show it better, and then we have a chance.
Another question online, can the double-double approach be easily integrated into a laminate finite element analysis model?
Yes, it's very easy. It's the same finite element analysis. You don't have to change. I mean, all the commercial software, and they can do double just as easily. It's the same thing as the quad. So there's no intrinsically there's no problem. Yeah.
Other questions?
Does double-double have an application for space travel?
Well, double has space travel, the Mars mission that SpaceX is doing, they rely a lot on stainless steel. In fact, our stainless steel had a lot to do with which is SpaceX. SpaceX changed the. I'm sure all of you have seen what SpaceX can do in these big rockets, and they can do miraculous things, how to recover them, how to reuse them. And so for space travel, for the rockets is not, but for the rest of it, they're all composites. We work very closely with the Jet Propulsion Lab. We work with, for example, lunar helicopters. So you know, it's okay to land on the moon, but then you want to look around, and you need helicopters, so you have to know how to. And we recommend to JPL to use double because double is much lighter and much easier to do. So in the Mars mission, and also for the materials, for example, when you have zero thermal expansion, which is very good because you do satellite, you zero because when the satellite goes between the sunny side and the shady side, there's a huge temperature difference. So your structure will expand or shrink depending on which side. But if you use a zero thermal expansion, and you use that for your helicopter, for your telescope or for your communication, it's a stable structure. It doesn't change. So the zero is very good, and also negative will do the shrink. So it opens up opportunities, and that we are working with JPL on that.
What is your opinion on thermoplastic matrix composites as an avenue to reduce fastener complexity?
We think thermoplastics has many advantages, and but is expensive at this point, more so than thermosets. So I think all the companies are looking at thermoplastics, and I don't know has something how it will come out in the future. I think that thermosets like epoxy, that's what people use, has a problem. How do you dispose of them? It's really a problem. You know, they grind it up. You can see an airplane. You have to grind it, and so there are issues. And the thermoplastic is supposed to. Thermoplastics are used in the smaller parts, like athletic shoes, and or many medical devices. They use thermoplastics, but building a 787 out of thermoplastics we're not there yet. So it's different.
Maybe just one
Last
more.
question.
Last question.
What are your thoughts on applying the double structure to watercraft, like a canoe, paddleboard, or surf skis?
Well, any structure you can apply. There's no, I mean, from serve board or something, a double or ski poles. A double advantage is can give you a lighter structure or a stronger structure. And we are working, for example, with the golf shaft company. We think we can make a better golf shaft. The key is tapering. Just remember the pancakes. You can taper so the golf shafts is taper only in the diameters, but you can do more than that. You can change the thickness. You can optimize it, and the double allows you to do that, whereas a quad you cannot. So if you have a taper, say how much weight can you save? Well, you can save a lot of weight, but in some cases, golf shafts, you don't need to save weight, but you want to make a drive longer, and you can manipulate the response of the shaft with greater flexibility with a double than you can do with a quad. But I'm not a designer of the shaft. I mean golf shafts or bicycle. But for example, bicycle, they want to make a light. I don't know what the lightest frame is now. It used to be something like 400 grams for the frame of a bicycle, which is the lightest. But they didn't use double, and they didn't use taper. So if they switch to double and taper it, they can do they can do half. They can go from 450 to 300, and so the opportunity is there, and so people don't use double. There are two principal reasons. One is they don't have supporting data. And so I show the new strategy. If you know what all those material laminate combination, you should have confidence in what materials. You don't have to spend millions of dollars to test every combination and so forth. But if you know what they should be, it simplifies. So that's one thing. So the lack of data, we don't believe is a valid argument. The other thing is that you have to study. And nobody likes to study, because it's hard. You have to learn something new, and all you can see is a risk. See, suppose something goes wrong. I'm sure there's always a risk you do something different. If you don't change it, then you don't get blamed. But if you change and it happens, then you're in trouble. So I think those are the two things.
And that's an excellent way to encourage people to take a risk, to change is hard. And that's a human condition. But I think getting to hear your story gives everybody inspiration on the future and what they can do to contribute to it by being willing to take risk and try new things. So it's an inspiration. So thank you so much.